So welcome everyone at the next session. In this session, we'll continue talking about forward kinematics. We stopped here the last session, and I said basically that for forward kinematics, basically what is important is to consider the input variables to basically, let's say, to manipulator or to the mechanism, and the target position. So the input parameters or the input variables could be rotational or sliding parameters. So rotational are for rotational joints or revolute joints, and basically displacement, you can consider parameters. They are for sliding movement or for sliding joint or for prisms, for example. Now, the target position is the target or the end effector position, which is our reference point in robotics and basically in manipulator mainly. Now, one of the algorithms that is actually common and yeah, it's actually the most used one, I would say, is called the Dinavet-Hartenberg or the DH parameters algorithm, which is used to basically to model forward kinematics of, or to have, or actually to get the forward kinematics model of a robot arm. Now for the DH parameter, and we will see in the next session something called DH2, which is basically similar, but the way these parameters are estimated is different. For both DH1 and DH2, we have four main parameters. These four main parameters are described basically, first they are denoted by A, alpha, theta, and S. Now the alpha and theta, basically they are two rotational, and we have two distance or two displacement parameters. First, what we want to achieve, just for you to know, basically that we have a reference, right, coordinate system, and we have basically the origin coordinate system. So this is the end effector, and this is the origin, or this is basically, you could call it this is going to call it the target, and this is the reference. So actually the reference is the origin, and this is the target or the end effector coordinates. Now we want to do matrix transform, or we want to get the matrix transformation that transform the coordinate of any point, let's say, from either from the reference to the target or from the target to the reference. So this is basically our goal. Now, of course, if we have only let's say one arm or one link in this mechanism or this robot arm, which, let's say, this is the only link we have beside, of course, the frame or the base, then you have only one transformation. We would have only one transformation matrix. If we have two joints, we would have, this is the first joint, the second joint, we have two transformations. Okay. Now here we see like an example of two joints, and which you can use it to generalize for other or for basically higher degree of freedom or for more joints. This is basically, you would see it always when robot arms, that first we have frame and we have the first link. Now there's the first joint here, and it's very common that the first joint is first has 1 degree of freedom, which is rotational degree of freedom, and can only rotate around the z-axis. Okay, because it's need to explore, let's say this is the working space of the robot arm, it's called, and it's basically, by this rotation, it's rotating and exploring the working space. Okay, so depending on basically the freedom or basically the constraints of this joint, it could basically, this working space could be either 180 degree, it's hard to have 360 degree, but some they have it, but basically the most common is 180 degree. Now I'll show you later some examples within Blender, just to see what I mean by working space and so on. But it's common, as I said, the first joint to have rotation around Z. Now the second around the z basically, which is toward where basically z is toward basically the up direction or the upward direction. And this is x0 and xy, and this basically, so this basically is 0 and xy, sorry, x0 and xy. They represent the basically the reference plane or the surface that this robot arm is set it on. Okay, and then we have x0 and xy that or y0, sorry, that they represent this plane, and we have z0, which is perpendicular to that plane, and the first joint is rotating around it. Now it's always this also for you need to know is that for all joints the rotational is mainly around the z. So for example, if we look now at the second joint, which is this one, and in this basically joint this link is rotating up or down. And here we see that we have rotations. That's basically the rotational angle that is bringing this up or down. And we see here that z1, so this is now this basically the second coordinate system, or you can consider the first coordinate system after the reference. And this is the rotation around z. That means this is the z-axis, and this is x1, y1. Now, first thing to consider here that this is basically was x0, y0, and z0, and now we have z1, x1, and y1. So what happened is that we have transformation, and the first transformation we had is that let's say we translated this coordinate system, so we moved it up by L1, then we did the rotation around x, right, because the z was in this direction, and then we rotated basically with 90 degree. So we had translation, then rotation. Now for the next basically for next coordinate system, we have, if we look here, only translation. So we translated only along x1 without rotation, because now z1 and z2 they are still in parallel, and this basically now x2, y2, z2. Now it is common that the also the end effector would have probably z directed up like the reference, so sometimes you could see that there's translation and rotation again. So this why these four parameters, they represent first of all only rotation and translation, because you have basically these two operations, or these two transformations that you need to do to transform from one coordinate system to the other. Now it's important to consider here that these four parameters, they describe the transformation from one coordinate to the other, so only two pairs of coordinate systems, which means two joints. Okay, so from first joint to the second joint, and so on. All right, so this is basically one important thing to consider. Now these parameters, they have two index, as you see, which is I and I plus 1, and I is the index of the first coordinate system, which let's say here would be 0, and x1, y1, z1 is would be 1. So the first would be a01, alpha 01, theta 01, and s01, which this, and by these four parameters we can first as we see in next slide, we could have the first transformation matrix that represents the transformation from this axis to this axis, or from this coordinate to this coordinate, and then we can have the second set of parameters which represent from 1 to 2, 1 to 2, 1 to 2, which basically describing from here to here. All right, so this is basically what these parameters represent. Now how we can, or actually what exactly they present, let's read the description. So we have the first distance parameter, or first displacement parameter, which is a which is described by a. Now it is a distance along so first of all, why we have four parameters before I starting describing, because we have seen here we first made the translation along the z-axis, then we had rotation around x-axis, then we had another translation along x-axis, then we might have again rotation around X, or we could have rotation around Z. So this is basically, it's trying to simplify it to have only 4 parameters where you can either translate along Z axis or rotate around, so you can either translate along X or Z, and you can either rotate around Z or X. Okay, so Y here kind of excluded, just to simplify. And we have seen with Euler angles that considering only 2 axes is enough to reach your target orientation. So so if we look here, basically, so the first here angle represent the distance from X or distance along X. So basically the distance along the X axis, which basically an example of that would be here, because we have this distance, and the distance here is L2, which represents here A. So the distance along X I plus 1. So for example, in this case where we have from 1 to 2, so the distance along x2, which is basically the same as x1 because they are on the same axis, from z1 to z2. So this is basically z1 to z2, and the distance between z1 and z2 is L2, which is basically representing here A. Okay, what is important is what you see here, the sign taken from the sense of x2. So which means that I have to basically, so the direction is along x2 and the sign is from along x2. Okay, which means if x2 is in the other direction, let's say, and then this would be, so it would be then negative if, for example, if x2 is in this direction. But this, you will never see this case, so most of the time they are in the same direction. Now the second is rotational, which is the angle from the positive z1 to, for example, let's say, because here we have rotation around x, which what we have done here. So let's take this example. So we have the angle from the positive z0 here to positive z1. Taking positive counterclockwise as seen from the positive along x1. Okay, so that means if I am so first of all, we have the here alpha represent the angle between z0 and z1. Okay, which means the first orientation we did here to, or the orientation we did here to basically bring z1 into this direction, because the rotation should be around z. And here we look, for example, that it is the angle between z0 and z1. This was the first thing we need to consider. As I am looking first from the direction of x1, okay, so let's say I'm looking from this side. So I'm looking at the mechanism from this side. Then I look, so I have this angle between these two. The positive would be basically the counterclockwise. So if this angle is positive from the counterclockwise, for example, here we have, this is the counterclockwise, and this is a 90-degree positive through the counterclockwise, which means we have here plus 90 that need to be considered. Okay, and this is the orientation between z0 and z1. Now, yeah, so the next one basically describe the orientation between x0 and x1. So this is in case there is orientation in this case, and you would also need to consider as you are looking from z, but here z0. And the next one would be, we would see an example of this. The next one would be the distance along z0, which is basically represent L1 actually, from x0 to x1, as I am looking from z0, which is basically, this is the distance. Okay, so these are 4 parameters. They might be a bit confusing, so you need to look at them multiple times and have some examples. And basically, yeah, and you need to you know how to use them. So just here we have to remark that in case joint is revolute, Then basically there are three parameters are constant, which is A, alpha, and S. And theta is the variable that is representing actually the input from the actuator, because we have rotational. Now in case of prismatic joints, all these three are static or constant, and this is basically a variable that is representing the movement of the prism joint. Okay, so this is basically this is the standard representation of DH parameters. That, for example, this we have, for example, the joint I minus 1, joint I, and joint I plus 1. And this is just explaining the transformation between the joint, and this is the distances. I find this is more explainable, but you can, if you see this, don't worry. Just basically represent what we have talked about here and there. Now, how to use these parameters? Why I need these four parameters? Because if I define these four parameters, I can now define the transformation matrix between, for example, the coordinate system I and I plus 1. So here between, for example, we have transformation matrix from I to I plus 1, and this is the standard DH parameters matrix, transformation matrix. So once I have these four parameters, I need just to fill it here, and basically you would get the transformation matrix between for example, I and I plus 1. For example, if I have only rotation around Z axis, which means this and this and this are, so I have no translation, nothing else, only rotation around Z axis, which might happen, or which actually has happened on most of them in this case, because here, yes, I have x0, x1, of x0, z0, and y0. Now here there is another coordinate system that we ignored, but actually it should be considered in the robot arm, and we will see it with the real robot arm later. It is, you can consider it actually the first coordinate system, and you can consider it as x1, y1, z1, and this should be 2 and this should be 3. Now x1, y1, z1 is, so the x and y are here again on the plane, and z1 is here, but the difference is that there is a rotation, because I am only rotating around the z. So x1 and y1 would create rotation, and of course z0 and z1 would be always aligned. So if I look back at this example, this is what I'm talking about here. So this is basically the z-axis, and I have only rotation in this plane. So x1 and z0 there, they create angles, which is the same angle between y0 and y1, and this is only rotation around the z-axis. So if I have only rotation around the z-axis, which means I have no translations and I have no rotations around the x-axis. So the only meaningful parameter would be their theta, and the rest would be zeros. And what we would get actually is for example, here we talked about if I have rotation around Z, you would get this is the result would be of DH parameters, or the DH transformation matrix. So if I just put that, so if I have only theta there and everything would be 0, you would get that transformation matrix. And this is basically what I meant there. And this is basically what this matrix would represent. If I have other parameters, then I can also fill it there. Now, what is important to know now, okay, I have two joints. For example, one, if you can start from 0, you can start, or 1, 2, this depends. But let's say this is the first transformation that is transforming 1 to 2. Then I have another transformation matrix for the next pair of joints, which from 2 to 3 until we get to the end effector. Okay, so this is basically the idea. And no, sorry, this is the end effector and this is the reference. Okay, so just for you to know, so it's basically the reference and this mode transformation that would end up with the end effector. Yeah, so And this is really the essence of the DH parameter, and this is a forward kinematics. We need to get these parameters that are transforming from one joint to the other joint. And by having these parameters, we can define the forward kinematic model, which is this one, which is basically a set of transformation matrices. And once we multiply them, we would get basically the final transformation matrix, which represent the forward kinematic model. Now, later we will see the inverse kinematic, which basically goes in the other way around. And we mainly will start with the forward kinematic model to get the inverse kinematic. Here we have basically example and then homework. So, and this would be your last homework, by the way. This basically example 5. So we have here a microbot model, which is basically a robot arm. And here we have the example and the solution. So we have a set of transformation matrices, as you see, which is 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. And we have here, this is just basically the after multiplication, which means this is 1 to 3, which is basically after multiplying these two matrices. This is 1 to 4 after multiplying 1 to 2, 2 to 3, and 3 to 4. And this is 1 to 6 after multiplying all together. And here basically how we do, then we multiply this with the transformation, which is basically with the current system, to get the end effector position with respect to the origin. So what is happening here? We have this robot arm. We have first x1, y1, z1, and we have the first rotation here, which is, as I showed you before, that could rotate around the z-axis. As I said, this is the common approach, or that the first joint is rotating around z-axis. And we have here these DH parameters that are defined. So we have the transformation parameters from 1 to 2, which are described in this 4, and 2 to 3, now described in this row, and so on. So if we look at the first basically row, which is from 1 to 2, we look here that basically this is z1, x1, y1, and this is basically z2. Now if you look at I don't know, some robot arms descriptions or manual, you could see some kind of difficult representation where you need to guess some of the axes, but it's always important. What is important actually is z always, because if z is here, as I said, the rotation is always around z. That means we have this rotational, and here we have z1, of course, because the rotation is around z1, and it's z3, z4, then we have z5, and we have z6. So basically z6 is the end effector position, which is here we have the origin of 6. z5 would be here. Okay, so this basically just the z6 is only translated because the end effector position is somewhere in this space. It's not on the robot arm. We have the origin, basically the current actuator values, which is basically here phi1, phi2, phi3, phi4, and phi5. We have the dimensions. This is basically 5 and not theta. Theta is here, would be basically calculated from 5. Now let's look, for example, at first parameter, which is a. From 1 to 2. Now a is, we said, is the translation or the distance or translation along x. So there we have 1 to 2, which means along x2, right, from z1 to z2. So if I look here back, this is z1 and this is z2, and translation along x2 basically, and x2 would be in this direction. But anyway, z1 and z2, if I look at them, they are on the same plane. They actually form a plane. That means there's no distance between them. That means if there's no distance between z1 and z2, that means a is 0. Now regarding alpha, which is the angle between Z1 and Z2, it's clearly is 90 degrees because this is Z1 and Z2. Theta, which is basically theta 1, 2, which is the orientation around Z1, okay, which is basically describe the input variable that is rotating this joint, which is now 30 degrees at this position, but this is a variable, so I can rotate it basically this way. It would be always a variable, but in current position it's equal to 30 degrees. And now S, which is the last one, which is a translation, and there actually it is the distance between x1 and x2 along Z1. So you can look back at the part of the description, and it's basically S, what is a 7-inch, which is given, which is basically is the distance between here to there. Now in the second row, it will be between 2 and 3. For example, the distance between, for example, we have A here, 7-inch. A is always the distance between the Z axes, and S is always the distance between X axes, just always remember. And theta is always rotation around the Z axis, and basically alpha is rotating around X axis. Now here I have, look directly, we have Z2 and Z3, and there is a distance between them, and this distance is represented by A23. We have here the rotation around X. There is no rotation around X, that's why it is 0. There is rotation around Z though, which is basically described by the 2, 3 there, which is a 60 degree. And there is no distance between the X axes because they are basically on the same plane. Now this is basically the same would be for the next joint. The as I said, for the 5 to 6, the only difference is that we translate from 5 to 6. So basically the idea here, or actually just what is happening there, is that number 6 is the point, let's say, in the 3D space that this robot arm need to reach, because here we have we have origin 6, and this is basically the point, let's say, that this robot arm need to reach, and it is basically has a distance from the origin 5, which is 3.8 inch. So 5, as it's not drawn here, which is basically make it of course more coordinate, more complicated. So you see here basically that 5 and 6, they are the same coordinates, but 6 is translated along Z. So, and it's described by 3.8 inch. And the idea is for kinematic is that, okay, if I have this now transformation matrix between 1, 2, 6, and there is now the question is the absolute position of the specified tool point now is determined by 2.5, which represent actually the point 6. Then what I do is I multiply this with the transformation. So this is basically now the position of the point 6, and if multiply then I get the position of x6, y, or the point 6 with respect to the origin, which is with respect to that means, for example, this point is 11 inch along the x-axis, so along this direction. It is 6 inch along y-axis, and also 11.7 inch along the z-axis, z1 axis. Okay, this transformed back to that coordinate system. Okay, so this is basically your homework, which is another mechanism. Here the axes are a bit more clear, and it's a bit simpler than this one. You need to do the same. So for each pair of joints, you need to define the DH parameters like here. So you need to have a table, and then there basically you need to model or first derive the transformation matrices, then multiply them, then you can derive the basically the full transformation matrix from the origin to the target or to the end effector. Now in the next session I will give more examples, which you can find it in one of the papers, about other mechanisms or other robot arms. So this is not the end for kinematic. Okay, thank you.